Hey guys, I remembered my password. Now, this video was originally written for a math assessment, so it's a bit different from whatever you want to call what I've posted here. Anyway, enjoy. Also, voice reveal, I guess.
Hey guys, in this video I'll be using ZSnout's Fractal Explorer to examine the creation and behavior of a multibrot set member fractal through a fractal zoom of sorts. Let's begin. Cue the music. Wait, hang on. I should probably explain what that means. Let me rewind a bit. There we go. Now, what was I going on about at the start? Let me explain. So, let's talk about the multibrot sets. These are a collection of fractals which are generated by mathematical functions, specifically functions of this form. An example of this can be seen in the Mandelbrot set, which is generated by this equation. My fractal is also a member of the multibrot sets, and is generated by this equation. Now, what this equation does is that it takes a seed value, in this case c, and iterates from z equals 0 using this function. So, the first iteration would be this, then this, and so on, and so on, and so forth. Now the colours are dependent on the modulus of z, specifically if it stays below 2 or diverges to infinity. If it stays below 2, the point will be black, and if it doesn't, it will be coloured depending on how fast it diverges. In this case, 2 is decided as the boundary, but it can be changed depending on what you want it to be. Now, something cool that you can do with this software is that you can customize the equation that you want to use. So here's my equation, and let's say for some reason you wanted to see a circle transform into this fractal. All you need to do is multiply the constant by s, which creates a slider between 0 and 1. Let's see it in action. This means that the constant value is multiplied by a number between 0 and 1, which transforms the figure from a circle to a fractal. Let's put that away for now. So, how did I come up with this function? Well, during my research I heard about multibrot sets, which is related to the Mandelbrot set. Why? Because the Mandelbrot set is a multibrot set member. What? Anyway, my function is based on the multibrot set expression by simply replacing the k with a 5. This expression creates a fractal similar to the Mandelbrot set, but with fourfold rotational symmetry, like a square or an asteroid. You know what? That was a lot of information to digest, and you will be getting some homework after this video, of course, so why don't we just relax with some more fractal zoom action? I'll come back when there's an interesting part. Hold up, go back. There. That's a corner. With self-similarity? Yeah, no, we're going back to math now. Now, what is self-similarity? Well, it's a property of fractals, which basically means that parts of it will be similar to the whole shape. Basically, these parts look like circular nodes, and if you look really closely, you'll see that this shape is repeated all along the surface. This is the backbone of self-similarity, as each of the nodes resemble each other at different scales. This can also be seen in the whole fractal, where the 4 main nodes resemble the smaller ones. You know what? I think it's time for another fractal break. Let's load it in. How can we improve this fractal? Well, there are sliders in the menu which can be adjusted. Let's adjust them. You know what? I don't like the lack of detail in this part. Let's increase it. This slider increases the amount of iterations calculated from 10 to 1000. let's crank it to 1000. Now, the software is calculating 1000 iterations of the fractal at once, which improves the detail of the fractal at the price of being a bit slower. Let's adjust the colors. This part will get flashy and there will be flickering colors. If you remember the seizure warning from the start, this is the part where it really kicks in. If this affects you, skip to this part of the video. Firstly, there are different color modes for the points in the background of figure, as well as alternate colors. Let's run over them quickly. The alternate colors do have duplicates, so I'll read them out once. They are: background changes color based on escape rate, background changes color based on path and final value, background hue changes based on direction, darkness changes based on distance from the origin, background changes color based on escape rate, but a lot more subtly, you'd have to zoom in to see it, black background, nothing at all, black fractal, fractal changes color based on path and final value, fractal hue changes based on direction, darkness changes based on distance from the origin, fractal color changes based on calculations involving the path, the software does not explain the calculations, splits the background colors into subregions, makes the background dark, makes the fractal white, splits the fractal colors into subregions, and alternate calculations for the colors of the background of fractal. Secondly, there's hue offset. This is based on the hue wheel, where 0 degrees corresponds to red, 120 corresponds to green, and 240 corresponds to blue. The number is then added to the original hue value, which means that you could see it cycling from red through the other colors and then back to red at 360 degrees. Then there's spectrum, or how much of it is used. At 0%, it's only red, and at 100%, the whole spectrum is used. Then there's the number of colors, which shows how many colors are used. This ranges from 2 colors to all of them. And decimal points change the position of the colors relative to the shape. Finally, there's repetition, which is how much the colors repeat themselves. This ranges from 10% to 999%, which can be described quantitatively as no noticeable repetition to a vast amount of repetition. Additionally, there's this side button, which just changes the colors used. Now, let's adjust the size slider. This adjusts the escape modulus, or more simply, it changes the distance that an iteration must be from the origin to escape the set. Let's set it to 100. This means that for a point to escape the set and be colored, there must be at least one iteration which exceeds 100 in magnitude. This has the added effect of changing the colors of the escaped points, as the amount of iterations it takes to escape will inevitably change. Well, that's all I can really do here. There's not much more math to explain, so I guess this is where the video ends. Thanks for watching, by the way.
So that's the video. Hope you liked it. Now on to your homework.